Hello everyone. In this lesson, I'm going to discuss rheology. We already understand that Hooke's law describes the relationship between stress and strain in elastic materials. In addition to elastic behaviors, there are other relationships between stress and strain. In the broader sense, rheology means the theory of material deformation, like Rheology of the Earth. It's the name of a book by Ranani, published in 1995. In the narrow sense, the term rheology stands for the relationship between stress, strain, and/or strain rate. These relations are expressed as mathematical equations called rheological equations, constitutive equations, or flow laws. Other variables like temperature, pressure, fluid activity may also occur in rheological equations. Rheological or constitutive equations are material dependent. They are different from equations for universal physical laws like the stress equilibrium equations. The latter are called universal equations. Universal equations must be obeyed by all materials equally, whereas rheological or constitutive equations are material specific. The rheological equation for granite under certain PT condition will be different from the rheological equation for marble under the same pressure and temperature condition, for instance. The term rheology was created about 100 years ago by Bingham. Bingham's original intention was to create a new branch of physics, although that branch of physics already existed, and it was called the mechanics of continuous media or mechanics of continua. Bingham thought rheology is a more friendly term for chemists. Rheology literally means everything flows. Rheological behaviors of real materials are complicated and are very rich. There are a few end members, and these end members can be understood using simple models. The elastic behavior can be visualized as an elastic spring. Plastic behavior can be visualized as a mass on a frictional surface, and viscous behavior can be thought of as a despot. So in an elastic spring, when stress is applied, elastic strain occurs, and when the stress is removed, the elastic strain is recovered. In a plastic situation, when stress is applied, nothing happens until the stress reaches a threshold. We say the system yields, the material yields. The stress beyond that is not possible because the system is already yielded. The stress is limited by the yield strength of the system. Such a behavior is called rigid plastic. A more realistic situation is that the system actually undergoes elastic deformation before it yields. So this is a better representation of a real material, a mass on a frictional surface in serial connection to an elastic spring, and this is called elastoplastic sometimes. A dashpot is made of a cylinder. It's made of a sealed cylinder with fluids. The cylinder has a piston which has many holes built into the piston. As an applied force is applied to move the piston, fluid from one side of the piston must move to the other side of the piston through those holes. And depending on the applied load, the piston may move faster or slower. So the stress is not related to the amount of strain, but to how fast you increase the strain. That's the viscous behavior. So these behaviors can be written mathematically. The elastic behavior stress is linearly related to strength by stiffness, elastic stiffness. So this is the general relationship. And the rigid plastic behavior is the stress has to be below the yield stress. And in the viscous situation, stress is related to the speed of strand, strand rate. Strand with a dot on top means the rate of strand. And the coefficient is called Newtonian viscosity, that we will talk about later on. If we put an elastic spring into the rigid plasticity, and then the system becomes elastoplastic. So it will deform as an elastic material as long as the stress is below the yield stress. As geologists, it may occur to you that elastic behavior is irrelevant because elastic strengths are not recorded in rocks. That thinking is wrong. First, elastic deformation is significant in the upper brittle lithosphere. Second, permanent deformations are always achieved by accumulation of infinitesimal strengths. So plastic strengths can be viewed as continual deposits of infinitesimal elastic strengths. The accumulation of infinitesimal slips gives rise to the geologically recorded fault slip. There are two contrasting conceptions about lithospheric deformation. One is that the ductile lithosphere deformation is homogeneous and broadly distributed, whereas the upper lithosphere deforms elastically and deposits elastic strand into permanent fault slip episodically. The other view is that the deformation in the ductile lithosphere remains localized as shear zones. The first view leads to a very low strand rate estimate for the ductile lithosphere, and the second view leads to a much higher strand rate for the ductile lithosphere. Geological records are more consistent with a localized deformation in the ductile lithosphere. The two views produces the same upper lithosphere behavior, so it is not possible to distinguish two behaviors through GPS data. The GPS data from St. Andrews Fault and the Alpine Fault in New Zealand give the same slip behaviors of the upper crust, regardless of whether the deformation is localized or distributed in the ductile lithosphere. Rheologists, material scientists, and geologists alike have adopted combined models to represent the rich behavior of the deformation in their fields. These models have gotten their specific names, so they are called rheological models. So plastic behavior in serial connection with an elastic spring is called a Moore-Coulomb model. An elastic spring in serial connection with a viscous dashpot forms a viscoelastic behavior. It's called a Maxwell model. An elastic spring in parallel connection with a dashpot is called a Kelvin model. And the Kelvin model in serial connection with a Maxwell model forms a Burgers model. And the Burgers model in combination with a Moore-Coulomb model forms what is called the Burger-Kripp viscoplastic model. What is a good model for Earth, for the lithosphere? Well, the model has to capture the following behaviors. First, Earth must be elastic on a short time scale. In response to a transient load, like an earthquake, the behavior must be viscous on a very long time scale, on a geological time scale, and the Earth's lithosphere must have an ultimate yield strength. Combining all these requirements, we can think of this model. Plastic device in serial connection with a viscous dashpot and with an elastic spring. This model should capture these characteristics of the lithospheric behavior. Under a transient load, the behavior is elastic. The instantaneous behavior is inelastic. The long-term behavior is viscous. And the stress must be below a threshold. Otherwise, the system will fail. Such a model is sometimes called a viscous plastic model. So viscous here, plastic. Here, plastic means it's elastic plastic, so it's not rigid plastic. In mechanics, these rheological models must all be formulated in mathematical equations, of course. We are going to cover more about rheology in the later sessions of this course. That is my brief introduction today. Thank you for your attention.